Okay, hello everyone. So one of the things that I know about when configuring remote execution system is how important it is for the right setup of your workers. So this is why I'm particularly excited to introduce to you Ulf Adams, who will be giving a talk today on 2 times faster builds with remote persistent workers.
Hey everyone, thanks for coming. Yeah, this is what I'm going to be talking about today. If you don't know me, I previously worked at Google. I left Google last year to work at EdgeFlow. At Google, I was I worked on the Bazel team, and I was sort of the tech lead for a long time. So I'm hoping to bring in some of the history of Bazel here as well. So let's get started. So, about a year ago, I was working on remote execution, and I wanted to see how well are we doing. So, let's set this up. Let's do a local build versus a remote build and see how it's going. I was using my local workstation, which is a fairly beefy machine, and then I didn't want to use the entire machine for this test, so I restricted Bazel to 8 parallel jobs, and then on the other side I ran a local instance of our remote execution service, and I restricted sort of the worker to at most 8 cores actually. So the worker is actually enforcing that every action running in the worker can only use a single core, using that, doing that using CPU sets. So let's give it a try. Let's run Bazel first locally with jobs equals 8, and the software, the open source project that I'm building here happens to be Bazel because that's what I'm familiar with. We'll get to more details later. All right, let's do the build. It takes 292 seconds, almost 300 seconds. So now let's run this remotely. The command line looks only a little bit different. The same 8 jobs, but now we pull in the configuration flags needed to use the remote executor. These are the usual suspects, setting the remote executor, updating like the strategies, using a Docker configuration. All of that stuff has to be enabled for remote execution. Not always. There is also a way to just run, remotely without all of that setup, but this is our default setup that we're typically using. And it takes, wait, what? 1,414 seconds. Well, that's unexpected. I mean, it's remote execution. Why isn't it faster? Okay. Let's look into this a little bit deeper. Okay, so let's bring up the profile. And if you've ever done Bazel profiling, you're familiar with this view. But you may also notice that this is not a Bazel profile. This is an EdgeFlow profile. So it's a profile that we collected on the back end. And what we're seeing here at very high level is there is a big block of things happening, and that's generally a good sign, right? You want the remote execution system to constantly be executing actions on up to 8 threads. That's how we configured it, and it shouldn't be doing any other weird stuff in the middle. Let's zoom in a little bit to see if that is accurate, and we can see here there isn't really much else going on. The pink blocks there all say execution time, which is sort of code word for it's actually running actions. But we can get a little bit more information out of this. So if we click on one of those actions, we can actually get information from the backend on what it was doing. And what we find here is it was running these actions in Docker. Okay, wait. Now, if we're running them in Docker, what that means in this case is we're spinning up a new Docker container for every action, and then we're shutting it down at the end. Now, that seems like it might be expensive. Maybe we can do better here. maybe we can reuse the Docker containers and not spin up new ones every time. So let's try that. And we get better results. We're now at 994 seconds, so still over 3 times slower than local build, but at least not quite as bad as before. So just reusing Docker containers saves us about, well, it saves us about like 30 to 40%, depending on how you compute it. So that's better, but that's still not good. So you know the answer to this question already. The answer is persistent workers, but let's talk a little bit about how we got there. So this was a couple of years ago when I was still working at Google. I was chilling in the office, and then suddenly email came in from another team at Google and said, Blaze is slow. Wait, no, that's not possible. Let me take a look here. Okay, so this was a team. They were running a Google production service, and they had a plugin system for their service where plugins could be written in Java of all languages. And so they were doing benchmarks with their system to see how fast can they make the turnaround time, right? They had like goals for, if someone makes a change to a module or a plugin, then, you have to rebuild and reload the plugin. And you want that to be as fast as possible. And so they were trying that, and they ended up at a number around, let's say 35 seconds. I'm not sure what the exact numbers were, but it was around that, sort of that order of magnitude. And so I looked at the setup a little bit more closely, and it turned out they were using very simple plugin, like more like a hello world than anything else, only consisting of 2 Java source files. And the 2 Java source files only had a couple of 100 lines each. But the time to compile these 2 Java source files was 30 seconds. So like easily the majority of the time that they had on their hands. And that was odd, right? If you change one of those Java files, you rebuild, it takes 30 seconds to rebuild those 2 files. And so, looking a little bit deeper, was Blaze contributing a lot of that time? No, the answer was no. Blaze was pretty fast. Blaze took, I don't know, like half a second or so. The majority of the time was actually spent in Java-C. Now, from Blaze perspective or Bazel perspective, we could always say, oh, not our problem, but that's not really a satisfying answer. And so I looked at the Java compiler, and I looked at what was happening there, and it turned out this plugin had a very large number of dependencies. So they had a lot of entries on the class path, and the majority of the time in the Java compiler was spent loading the class path. Now that seems like a waste, right? If you change a Java source file and you have to reload the class path, and you change it again, you have to reload the class path, and every time it takes 30 seconds. So that's not good. Is there anything we can do about that? Is there any tech out there that solves this problem? And it turns out there is tech, or there was tech at the time out there, in the form of a tool called sjavac. So this was a tool that Oracle used in upstream OpenJDK to make their OpenJDK builds faster. And the way it worked was it spawned a Java compiler process and then talked to it over a local TCP/IP socket to send it sort of new compile requests. Now, persistent workers, Blaze, hermeticity, let's give it a try. So I spent a week or two to put hacks on top of hacks, on top of even more hacks, on top of an OpenJDK patch, because that's what it took. And I got it to work. And after a bunch of testing and tweaking, we got it down to about 300 milliseconds for that build. So at that point, it was no longer reading the jar files every time, but it was spending most of the time actually in Java compilation. And so at that point, it became very clear to me that in some cases, making it possible for tools and compilers to keep state around is really, really useful, right? In this case, it was 2 orders of magnitude faster. That's there was no other change in Blaze that we ever made that okay, maybe there 1 or 2 changes in Blaze that we made that came close, but by and large, this is a rare opportunity where you can literally get, a factor of, sure, this is a special case, this isn't necessarily representative, but if we can get a factor of 3 or 4 out of it, that's amazing. You never, there are not many opportunities of this size. And so I didn't do the work, right? And no one should claim that I wrote persistent workers in Bazel. Most of the work was done by my colleague Philip Wallerman and others on the team. But yeah, persistent workers can make a pretty big difference. And so it looks like here we have one of those cases where Bazel locally uses persistent workers, and it makes it a lot faster compared to just running each action individually. So, persistent workers, remote execution. What a terrible idea. Let's give it a try. All right, we got it down. So Bazel didn't support this natively. So I wrote a patch for Bazel. So that's why you see the command line now uses a different Bazel binary. We put this patch on top of Bazel 4.1 for this example. The patch we've actually written it for Bazel, I think 3.2 or something, and we've been porting it forward since then. It's not included in Bazel upstream yet. We're working on that. That's something that we need to spend more time on and to make sure that we get it right. And so that that brings the compile time for Bazel down to 620 seconds, which is a lot better, right? We just shaved off 30% of our build time. So let's look at the numbers. The local build, again, was 292 seconds, almost 300 seconds. Then the remote build was a lot slower. But the first approximation, it turned out that starting and stopping Docker is very expensive. And so we've sort of fixed that. Got it down to 994 seconds. It's still 3 times slower than the local build. And then we enabled persistent workers, and that shaved off about 30% and brought us down to 620 seconds. Now, that still isn't 300 seconds. Can we get it down to 300 seconds? And I mean, you can see from the table here, we still have some aces to play. So let's look at the statistics here. So Bazel is running 2,666 actions, of which only 729 are viable for persistent workers. And out of those, only 523 is not bad, but maybe we can get that number higher. 523 actually reused a previous Java compiler or other persistent worker, right? Bazel has persistent workers for a lot of different things. I think in this case, it's mostly Java compilation. But persistent workers also exist for TypeScript, for Android, for Kotlin, for Scala, you name it. If it targets the JVM, it's very likely to have persistent worker support. If it doesn't target the JVM, it's pretty likely not to have persistent worker support. Well, there is also JavaScript, but yeah, who counts that? Okay, so can we do better here? How can we increase the number of reused workers? And the key insight here is we were running 8 actions on an 8-core cluster. And so basically, we're loading the cluster 100%. We're loading it to the limit. And in the service, that means if there is a persistent worker running in one of the slots, and a non-persistent worker action comes in, or one with a non-matching worker, then the service will shut down that worker and run that action, right? It won't leave slots idle if it can, if it has work to do. And that means that there is a pretty good chance that the workers get restarted. For Bazel locally, Bazel kind of cheats a little bit in that it will start a bunch of workers, and then it will keep them around while running other actions. It will only shut them down, in certain cases when it, has too many of them running and stuff like that. And so maybe we can get a more comparable case where we allow the remote execution system to keep a couple of those workers around, even when sort of the slots are used otherwise. And so let's start with 4, just because. So we can run 8 actions in parallel, and we can keep up to 4 additional workers running before the system will start shutting them down. And we run that again, and we get down to 460 seconds. Now, that's not bad. We're getting closer. We're not quite at 300 seconds yet, but we're getting there. So maybe 4 additional actions is enough. Maybe we can use 8. That shaves out off another 40 seconds or so. I don't have a slide for that. Well, not quite 300 seconds yet. There is one more thing here, which I want to mention, which is that when we enable remote execution in Bazel, the Bazel source tree is configured to use an auto configuration mechanism for the Docker containers that will download the Docker container and then run something inside of the Docker container to detect the tool chains and Java runtime and that kind of thing. And that step takes around 30 seconds. And so if we skip that and also use a warm cluster, right? So if we run this build on a remote execution cluster, then it will spin up a bunch of worker processes. And so if we run a second build after the first one, the second build can actually reuse the worker processes from the first one. So it doesn't have to spin up, the first few actions, it doesn't necessarily have to spin up new worker processes. And so if we combine that, we get it down to 368 seconds. Now, unfortunately, the way I did that is not entirely fair, because I didn't just skip the Docker auto configuration, I also skipped the analysis phase here. But this is what it could look like. This is sort of the order of magnitude that we expect here. So let's look at the numbers again. If we keep, there is this line +4, which is we keep up to 4 persistent worker processes around that may be idle. And we see that the number of reused workers goes up from 523 to 681. And we see that the time dropped by another 160 seconds, that's pretty good. And that's at the small price of 150 additional reused workers. So, we can estimate here, roughly, this isn't exact, but we can estimate here that we save about a second per persistent worker reuse. And then if we bring it up to 8, we actually reuse the existing persistent worker process 710 times. And if we rerun on the warm cluster that already has persistent worker processes running, we bring it up to 221 reused worker processes and a total time of 368 seconds. And so, of course, we have, one thing first. So I said, the title says 2 times faster persistent workers, but where is that number 2 coming from? All right, let's look at it. The number 2 comes from us comparing remote execution with persistent Docker. If you don't have persistent Docker, or if you don't run your actions locally, you're already paying like additional cost, and we don't count that here. This is just persistent workers, the improvements we get from persistent workers, and we compare that with the sort of the best case scenario where we keep up to 8 workers idle on the cluster that has 8 slots for action execution. And that gives us about a factor of 2, right? And in the warm case, we get a little bit more, we get like 2.5, 2.6. Now, this number is fairly representative. I can't give you all the numbers that we've collected over the past year, but we've run this with a number of production source code bases, and we have consistently seen about a factor of 2 if we make sure that the cluster has excess capacity where it can keep persistent workers running, rather than loading. We don't load the cluster to 100%. We make sure that it has additional capacity. One way to do that is to actually reserve machines just for persistent workers. That is very effective, of course, but it's also expensive. So it's a trade-off, and if you deploy this, you have to decide how you want to do it. All right, let's look at the graph. So we're approaching local build times, so that's good. We're not quite there yet, and so the question is, why is that? But before we get to that, why is this work important at all? Well, the main argument I can make is not every build can be parallelized. Sometimes the graph, the execution graph just isn't that wide. Sometimes, Bazel cannot easily split up actions. There are some corner cases, but in general, it can split up actions. If you run the Java compiler, you run the Java compiler, and you have to run it to completion. You can't, put it on 2 machines and then it's faster. That's not how it works. You can't, 2 chickens can't hatch an egg 2 times faster. That's just not how it works. And in particular, you sometimes have these builds where you have a chain of sequential actions that depend on each other. And the only thing you can do to make them faster is to make the actions faster. And this is especially true for incremental builds where a user comes and just modifies the source file, rebuilds that one library, rebuilds the next library, rebuilds the next library, rebuilds the binary. You want to make it faster, you have to make the actions faster. We also have to be clear about the limits of remote execution, right? It doesn't help us to say, oh, remote execution is awesome and you should always use it and it's always a win. It's not true. There are cases where remote execution is a net loss. It does have overheads, especially for incremental builds, but with the right tech, we can get pretty close. And certainly, from another perspective, you could say, but local build tools are cheating it. Sure, but that's got to stay around. No one's going to throw away a 4x performance improvement in their builds. That's just stupid. We can also look at this the other way around. So if persistent workers make your local builds 4 times faster and you can't use them remotely, you have to throw 4 times as many cores. That's a problem. And maybe you can do that at least to get to the same level of performance, right? If you locally build with a quad-core machine, your remote execution cluster needs to have 16 cores. Otherwise, you can't expect it to have similar performance because persistent workers are so incredibly effective for local builds. And sure, maybe you can afford that, which is fine. I won't blame you for spending more money on machines, but it's sort of a waste, right? It's the reason it's so slow is that it's doing a lot of duplicate work, and there are ways to avoid that duplicate work. So why shouldn't we? Are there other ways to achieve this? Maybe. The Java VM is designed to provide very good steady state performance, but not be very good at startup performance. And there are efforts with upstream in the OpenJDK project to change that, right? There are ways to compile Java code to native code. And now, unfortunately, the way that's currently done, you lose the steady state performance, right? You get better on startup, but you lose on the steady state. And if your binary runs for more than about a second, the steady state performance is more important than the startup performance, unfortunately. Now, for the Java compiler, might be worth it, might not be worth it. In many cases, the Java compiler actually, for a couple of files, it actually runs under a second. And so it might be worse compiling it to a native binary instead of using the interpreter to start it up. But it's also often the case that the Java compiler takes longer than a second, in which case you're better off with the JVM as it stands today, unless, of course, you can use persistent workers. But wait, what about hermeticity? Aren't we losing hermeticity? That's terrible, right? It's a trade-off. What can you do? Certainly, once you start doing this, it's even more important to do proper sandboxing, process control, and file system cleanup, right? You want to make sure that when you shut down your persistent worker, it's shut down, and that you clean up your file system even between individual actions within the persistent worker run. You can also see it differently. I mean, you sort of trust Bazel to provide that hermeticity. Now you also trust the compiler to provide that hermeticity. And to be fair, in our experience, right, since the Bazel team implemented persistent workers, we have not seen any major issues, at least with the Java compiler. I don't know about all of the persistent workers, but certainly the Java compiler is written to a very high standard, and it warrants trusting it to be correct. And then, of course, if you don't want to trust it, you can provide exceptions for cases where they're special. You can have an exception for release builds. You can say that you don't want to reuse workers across different users. You only want to reuse workers, for a single user. You don't want to reuse workers across teams. You don't want to reuse workers across multiple builds. It's still useful. The good news is, in our testing over the past year, we have never seen a case where persistent workers made the build slower. As long as you can reuse the persistent worker process at least once, you're good. And even if you can't reuse it, the overhead of managing the persistent worker process is basically negligible. All right, but that leaves the last question. Where did the rest of the time go? We're not at 300 seconds yet, so what's missing? Okay. Well, there are a number of factors, and I can't say right now exactly how large each of them are that would require more work. So there is general protocol overhead, right? We've already heard that yesterday from Arriver. Building Merkle trees is not cheap, especially when the input trees are large. Then there is a localhost round trip. It's very cheap, but it's not free. And we have a lot of round trips, right? For every action, we have at least 3 calls. Bazel to the scheduler to the worker. Actually, Bazel to the scheduler twice, because it first checks the action cache and then separately runs the action. And so that makes at least 3 calls to get any action running. And if we look at the profile, we can see that the gap between actions on the remote execution system is around 8 milliseconds, which is a lot higher than for local builds, which is less than a millisecond. Then, of course, we download the files. It's effectively a local file copy just over TCP/IP. In this specific scenario, certainly if you use a remote execution cluster that is actually remote, the downloads will actually be more expensive than local file copies. Now we can actually test this. I tested it in this case. It's too noisy. We can't measure the difference because the variance on the build time is higher than the difference in the download times. Then we have, on the remote execution system, we have to stage the input directory. We have to put all the files in the right places. We have to perform consistency checks. We have to put output files into storage, which at least requires hash computation. So, in order to put the output file into storage, we have to hash it. We have to put it into the cache. And we also have to, copy or move the file into wherever it's stored locally. And then, of course, the thing that I already alluded to earlier, Bazel doesn't enforce CPU limits. So when I run a local build with 8 jobs, Bazel can actually use all 16 cores. It's not limited in any way. Whereas in the remote execution case, the worker enforces that every action can only use exactly 1 core. So the local builds have a little bit of an advantage there. And that's also something we could test and see how much of a difference that makes. the Java compiler is multi-threaded. Every Java program is multi-threaded. Even Hello World is multi-threaded because the JVM is internally multi-threaded. And so anything that runs on the JVM can potentially benefit from having more than one core of CPU capacity available. And so, there are multiple ways we could test this. We could, we could actually change Bazel to enforce local CPU limits. We could change the setup in this case to allow bursting beyond a single CPU core if necessary. I didn't do that in this case, but this will, I'm fairly certain that we would see the times get closer to the local build case. So yeah, that's all. Thank you very much for listening. And if you have any questions, just type them into the question field on the right.
Ulf, thank you very much for all that detail. I very much appreciate how much kind of like time that you spend kind of profiling this and showing kind of like some of the limitations that we don't always appreciate when it comes to remote execution. So I think we've got time for maybe 1 or 2 questions, and then I think we've probably got a few more questions that maybe you could have a few minutes answering in the water cooler. That's okay.
Sure.
So the first one is, how does the Bazel client interact with the persistent workers running in the remote execution cluster? Were changes made to the remote execution API to support the interaction?
The good news is there were no changes to the remote execution API at all. The only thing we do in this case is we have Bazel tell the remote execution service that actions are persistent worker capable, and then the actual interaction and management of the persistent worker falls to the remote execution system. So it's I think it's a very clean design overall. The only thing we provide from Bazel's side is a couple of hints. This action can be run in a worker. This can't be run in a worker. If you run this in a worker, these are the files that are part of the worker process rather than inputs to the action. And that's enough for the remote execution system to do that. Now, I alluded to this earlier that our patch isn't quite ready yet. And that's because Bazel's API with remote persistent workers is actually fairly complex, and we haven't mapped everything to remote execution API properties yet. And so, there is support for protobus protocol, there is support for adjacent protocol, there is support for multiplex workers. Not everything is available in the remote execution system yet.
Thank you. I think we've got time for one very last quick question. In terms of the class path reloading, I think that was something that at the very start of the talk described as the bottleneck. So what was the overall source for that? Was it an IO cost, or was it compute as well?
That's a good question. I don't know. So I know at Google we have optimized. Google has a Java platform team that's working on the JDK, and they have optimized class path loading several times, and there were different things that they fixed. I can't say right now what the original source was, and I certainly hope that all the patches made it upstream. And it's possible that if we reran the same scenario today, that we wouldn't actually see it take 30 seconds to load all the jar files anymore, but maybe it would only take, I don't know, 3 seconds with all the all the fixes that were made in OpenJDK. So there you are. I don't know.
All right. I think we're out of time, I'm afraid, but thank you very much, Ulf.
Thank you.